The force responsible for stretching our universe appears to be losing its strength. For decades, we believed dark energy was a constant property of empty space, a fixed energy density that never changes. But data released earlier this year from the Dark Energy Spectroscopic Instrument, or DESI, suggests otherwise. This finding has triggered a 2026 cosmological crisis. If dark energy is not a constant, our standard model of the universe, Lambda CDM, is fundamentally incomplete. We are seeing hints that the vacuum itself might be evolving, meaning the fate of everything from galaxies to atoms depends on a dynamic field we don't yet understand. The anomaly isn't just a minor statistical flicker. The combined analysis of 15 million galaxies has yielded a preference for evolving dark energy with a significance between 2.8 and 4.2 sigma. While not yet the 5 sigma gold standard for a discovery, it is the most uncomfortable measurement in modern astronomy. To physicists, this signal suggests that dark energy might be weakening as the universe ages. Instead of a rigid cosmological constant, we might be looking at a dynamic field, sometimes called quintessence, that changes its density across cosmic time. This would require a total rewrite of general relativity at the largest scales. However, extraordinary claims require extraordinary confirmation. Critics argue that the current signal could be a result of undetected systematic biases in how we calibrate our cosmic rulers. We need a definitive tiebreaker, an instrument designed specifically to eliminate these errors by looking at the problem from 3 different angles simultaneously. That tiebreaker is the Nancy Grace Roman Space Telescope. As of April 2026, the observatory is fully integrated and undergoing its final environmental gauntlet at NASA's Goddard Space Flight Center. It is currently being subjected to the acoustic and thermal vacuum tests that will simulate its journey to deep space later this year. Roman is a measurement revolution, not just a larger camera. While it has the same crisp resolution as Hubble, its field of view is 100 times larger. This allows it to perform a cosmic census, capturing millions of galaxies in a single mosaic that would have taken Hubble nearly a century to map. Its strategy for settling the dark energy debate is ruthless. By combining weak gravitational lensing, standard rulers from the early universe, and the monitoring of thousands of supernovae, Roman can cross-check its own findings. If the DESI signal is real, Roman's data will be the first to move us past Einstein's constant. The urgency in 2026 is palpable because our current models are hitting a wall. The discrepancy between the expansion rate we see in the early universe and what we measure locally, the Hubble tension, has grown too large to ignore. A weakening dark energy field might actually be the missing link that resolves this gap. But to understand if dark energy is truly changing, we must first master the art of measuring the invisible. We have to understand the tools we use to weigh nothingness itself. If our standard ruler is broken, our entire map of the universe is a lie. To see how we know anything at all, we have to look at the yardsticks of the cosmos. To understand the crisis, we have to look at the 2 measuring tapes we use to gauge the universe. We cannot touch the vacuum, so we rely on markers that allow us to reconstruct expansion through light alone. The first marker is the standard candle, specifically Type 1a supernovae. These are white dwarf explosions that occur with a nearly identical peak brightness. Because their intrinsic light is constant, their apparent brightness reveals exactly how far away they are. By measuring redshift, the stretching of light into longer wavelengths, we can see how much space expanded while that light was in transit. This relationship between distance and speed first revealed that our universe's expansion was accelerating in the late 90s. But candles have limits. Distant light can be dimmed by dust, or the chemistry of ancient stars might differ from those today. To be certain, we need the standard ruler, a measurement that doesn't rely on the life cycles of stars. This ruler comes from baryon acoustic oscillations, or BAO. In the hot plasma after the Big Bang, sound waves traveled through the dense matter. These pressure waves pushed matter into massive concentric rings before the universe cooled and the pattern froze. These rings left a physical imprint on the cosmic web, creating a predictable separation of about 500 million light-years between galaxy clusters. This provides a massive, three-dimensional geometric scale that allows us to map the geometry of space itself. As of April 2026, the Dark Energy Spectroscopic Instrument, or DESI, has used these rulers to create the largest map of the cosmos ever assembled. DESI tracks millions of galaxies to measure expansion back to when the universe was young. The significance of the 2026 data lies in its precision. We now have a 4 sigma hint, a high confidence level, that the expansion rate has fluctuated. If confirmed, it suggests the force driving the expansion is not a fixed property of space. Reconstructing this history is a game of look-back time. When we observe a galaxy 10 billion light-years away, we see the universe as it was when dark energy was just beginning to overpower the pull of matter's gravity. The 2026 challenge is getting these candles and rulers to agree. If the distance measured by a supernova contradicts the distance measured by a galaxy cluster at the same redshift, our fundamental model of the vacuum is likely incomplete. This is why the Nancy Grace Roman Space Telescope is a revolution. Unlike previous missions, Roman is designed to perform both tests simultaneously, monitoring thousands of supernovae while mapping galactic rings across a massive swath of the deep sky. Now fully integrated at Goddard, Roman's wide field camera will capture these data points 100 times faster than Hubble. It is the ultimate cross-calibration tool, designed to eliminate the systematic errors that might be distorting our ground-based measurements. The relationship between distance and redshift is robust, yet the tension between our different tapes is reaching a breaking point. We are realizing that our most trusted measuring tools are telling two different stories about the same universe. These two tapes gave us a simple answer for decades. Dark energy is a constant, unchanging property of the vacuum. To see why this assumption was so successful for so long, we have to look at the Reign of Lambda. For 20 years, our best guess was that dark energy is an unchanging tax on every cubic meter of empty space. This is the cosmological constant, denoted by lambda. It suggests that as the universe expands and creates more space, the energy density stays exactly the same. This concept is the heart of the Lambda CDM model, which has served as the standard model of cosmology since the late 90s. It combines Einstein's constant with cold dark matter to describe a universe that is flat, dominated by dark components, and destined to expand forever. The brilliance of lambda lies in its simplicity. Instead of a complex field that interacts with matter, dark energy is treated as a fundamental property of the vacuum itself, the zero-point energy of empty space. In this view, space doesn't just contain energy, it is energy. We have incredibly strong evidence for this baseline. The Planck satellite's mapping of the cosmic microwave background provided a snapshot of the early universe that fits the Lambda CDM model to within 1%. It confirmed that dark energy accounts for roughly 68% of the cosmos. According to this model, the density of dark energy is incredibly low, about 10 to the negative 26th kilograms per cubic meter. While that sounds negligible, when multiplied by the vastness of the intergalactic void, it becomes the dominant force shaping the fate of galaxies. One of the most robust observations supporting this model is the flatness of the universe. Measurements of the early universe's light show that the total energy density, known as omega, is exactly 1. This geometric perfection is only possible if dark energy behaves as a constant. In mathematical terms, This is expressed through the equation of state, or W. If dark energy is a true cosmological constant, W must be exactly -1. For decades, every major survey from the Dark Energy Survey to early Euclid runs found W hovering right at that value. This consistency led to the prediction of a big freeze. In a lambda-dominated universe, the expansion accelerates at a steady, predictable rate until every galaxy outside our local group is pushed beyond our horizon, leaving us in a lonely, cold, and dark future. However, there is a giant skeleton in the closet: the cosmological constant problem. Quantum field theory predicts a vacuum energy density that is 120 orders of magnitude larger than what we actually observe. It is the largest discrepancy in the history of physics. Despite this theoretical embarrassment, scientists preferred Lambda CDM because it was the minimalist model. It required the fewest assumptions to explain how the universe evolved from a hot, dense soup into the complex web of galaxies we see through our telescopes today. It was the old model that worked everywhere, until recently. By 2026, the precision of our instruments has reached a point where the cracks in this elegant foundation are becoming impossible to ignore, particularly when comparing the early and late expansion rates. The DESI results from last year were the first to suggest that the value of W might actually be changing over time. If W is not -1, then lambda is not a constant, and our simplest model of the universe is fundamentally broken. This brings us to a conflict that has been simmering for a decade. The elegant picture worked perfectly until we looked closer at the expansion rate today versus the expansion rate in the early universe. The two numbers simply do not match. When our two best ways of measuring the universe's growth produce different results, we face a gap in our knowledge known as the Hubble Tension. To understand why this discrepancy might destroy our current physics, we have to look at the numbers ourselves. The first major crack in our understanding of the cosmos didn't come from a new mystery, but from a disagreement between two fundamentally different numbers. We call this the Hubble Tension, and by April 2026, it has become the most expensive paradox in the history of physics. When we look at the oldest light in the universe, the cosmic microwave background, our best models predict that space should be expanding at a rate of exactly 67.4 kilometers per second for every megaparsec. This is the top-down approach, rooted in the initial conditions of the Big Bang. But when we measure the distance to nearby galaxies using Cepheid variable stars and Type 1a supernovae, we get a consistently higher result, 73 kilometers per second. This bottom-up approach measures what is actually happening in the local universe right now, and the two numbers refuse to meet in the middle. For years, many researchers hoped this was simply a measurement error. Perhaps our calibration of Cepheid stars was slightly off, or perhaps dust in distant galaxies was distorting our view. However, as the datasets grew larger, the statistical gap between these two realities only widened. By 2025, the significance of this tension crossed the 5 sigma threshold. In particle physics, this is the gold standard for a discovery. It means there is less than a 1 in 3 million chance that this discrepancy is a coincidence or a fluke of the data. Recent high-resolution observations from the James Webb Space Telescope confirmed these local measurements were correct. JWST ruled out the possibility that Hubble's cameras were misinterpreting groups of stars as single sources. The local expansion rate is real, and the CMB prediction is also real. This means the Lambda CDM model, the bedrock of modern cosmology, is missing something fundamental. If dark energy is truly a constant, as the model assumes, these two measurements should be identical. The fact that they aren't suggests that dark energy has evolved since the dawn of time. One leading explanation for this tension is a theoretical phenomenon known as early dark energy. This hypothesis suggests that a brief burst of dark energy occurred shortly after the Big Bang, accelerating the expansion rate just enough to change the sound horizon we see in the CMB. If this brief burst occurred, it would resolve the mathematical conflict without throwing away Einstein's general relativity. But it would also mean that dark energy isn't a passive property of space. It's a dynamic player that can turn on and off across cosmic epochs. In early 2026, data from the Dark Energy Spectroscopic Instrument, or DESI, added another layer of complexity. Their massive survey of 40 million galaxies hinted that dark energy might be weakening in more recent times, further challenging the idea of a fixed cosmological constant. We are now in a situation where our two best measuring tapes don't agree, and our third and fourth tapes, DESI and Euclid, are showing signs of a changing universe. The tension isn't just a rounding error, it is a signal that our map of the universe is fundamentally incomplete. To break this tie, we don't just need a bigger telescope or a longer mission. We need a way to perform all these measurements simultaneously using the same instrument to eliminate the hidden systematic errors that currently divide the scientific community. The stakes couldn't be higher. If the tension is real and the constants are actually variables, then every prediction about the final fate of our universe, from the Big Freeze to the Big Rip, must be recalculated from scratch. How can one new mission observe 100 times more space than Hubble ever could, providing the massive census required to settle this debate? The answer lies in a design that prioritizes field of view over sheer magnification. It's time to meet the Nancy Grace Roman Space Telescope. To break the deadlock of the Hubble tension, we need more than a better telescope. We need a machine capable of a massive cosmic census. Meet the Nancy Grace Roman Space Telescope, NASA's next flagship mission. It is the observatory designed specifically to find out if the vacuum of space is actually changing. The story of Roman begins with a surprise gift from the National Reconnaissance Office. They donated two 2.4-meter primary mirrors originally intended for spy satellites. These optics are the same size as Hubble's, meaning Roman has the same razor-sharp vision, but with a vastly different mission objective. While Hubble was built to peer deep into tiny, keyhole-sized patches of the sky, Roman is built for the big picture. It carries the Wide Field Instrument, a 288-megapixel camera that captures an area 100 times larger than Hubble in every single exposure without losing any resolution. Imagine the iconic Hubble Ultra Deep Field, a tiny dot representing weeks of observation. Roman can capture that same detail across an area equivalent to 100 deep fields in a single shot. This massive field of view is what transforms cosmology from an anecdotal science into a statistical powerhouse. As of April 2026, the telescope is no longer a collection of blueprints. It is fully assembled and integrated at NASA's Goddard Space Flight Center in Maryland. The silver-colored wide-field instrument and the sophisticated coronagraph are now physically mated to the spacecraft bus, forming a single unified observatory. Right now, engineers are putting the telescope through its final environmental trials. This includes acoustic testing to ensure the hardware survives the roar of a Falcon Heavy launch, and thermal vacuum tests that simulate the extreme cold and radiation of its future home in deep space. Roman's primary weapon against dark energy is the High-Latitude Wide Area Survey. Over 5 years, it will map hundreds of millions of galaxies across a quarter of the sky. This isn't just a photo gallery, it's a high-definition 3D map of the universe's expansion history. To handle this, Roman will beam back roughly 1.4 terabytes of data every single day. This is a data volume so large that traditional analysis won't suffice.
The mission is pioneering AI-driven pipelines to identify patterns in galactic distributions that human eyes would simply miss. Unlike the James Webb Space Telescope, which looks through a thin straw to see the first stars, Roman is the panoramic lens of the cosmos. It finds the needles in the haystack, the rare supernovae and gravitational lenses that Webb can then follow up on with intense detail. By measuring expansion through 3 independent methods simultaneously, weak lensing, standard rulers, and standard candles, Roman eliminates the systematic errors that plague current experiments. It is the ultimate tiebreaker for the constant versus dynamic dark energy debate we face today. The mission is scheduled for a launch window between late 2026 and early 2027. It will head to the second Lagrange point, or L2, a stable gravitational pocket a million miles from Earth. From there, it will watch as the universe unfolds with unprecedented clarity. But the hardware is only half the battle. The true revolution lies in the data synergy between Roman and the European Euclid mission. Together, they are creating a cross-calibrated map of the dark universe that will leave no room for statistical fluke or measurement error. If the data from Roman confirms what the early 2026 hints from DESI and Euclid suggest, we are in for a shock. We would have to admit that the cosmological constant, the lambda we've relied on for decades, is fundamentally wrong. With the technology now tested and the launch on the horizon, the pressure is on the theorists. If the vacuum energy is indeed weakening, what kind of new dynamic physics is waiting in the wings to replace Einstein's constant? If the vacuum energy is indeed weakening, we are essentially choosing between 2 world-changing outcomes. Either there is a new force of nature, or Albert Einstein's description of gravity is incomplete at the largest scales. The first contender is quintessence, a hypothetical scalar field that permeates all of space. Unlike the static cosmological constant, quintessence is dynamic, meaning its energy density and its repulsive push on the universe can shift and decay over billions of years. Physicists track this behavior using the equation of state parameter, known as W. While Einstein's constant is locked permanently at -1, quintessence models allow W to be slightly higher or even evolve over time, matching the weakening hints we see in recent 2026 data. The second, more radical possibility is that gravity itself is changing. In modified gravity theories, like F of R gravity, the rules that govern how planets orbit stars don't perfectly apply when we look at the vast, empty voids between galaxy clusters across billions of light years. The technical challenge is that both quintessence and modified gravity can produce nearly identical expansion histories. To a standard survey, they both simply look like the universe is speeding up or slowing down at the same rate. To break this tie, the Roman Space Telescope is hunting for a specific number, the growth index, denoted by the Greek letter gamma. This parameter describes how quickly matter clumps together to form the massive cosmic web of galaxies we see today. Einstein's general relativity predicts that gamma should be exactly 0.55. If Roman measures anything else, like the 0.68 predicted by some alternative gravity models, it would be the smoking gun that our current laws of physics are just a local approximation. Roman measures this using a technique called weak gravitational lensing. It captures the subtle, microscopic distortions in the shapes of millions of distant galaxies caused by the invisible pull of dark matter intervening along the line of sight. By analyzing these distortions at different cosmic distances, or redshifts, Roman creates a high-resolution 3D map of how the clumpiness of the universe evolved. This is effectively the growth history of the cosmos, recorded in the shapes of the stars. This creates the ultimate growth versus expansion test.
If the expansion history looks like a constant, but the growth of structure deviates from 0.55, we know it is a failure of gravity, not a new energy field. The Wide Field Instrument is the mission's superpower here. While ground-based observatories like the Vera Rubin see more of the sky, Roman's position in space provides the Hubble-level clarity needed to detect distortions as small as 1 part in 1,000. This sub-pixel precision is vital for removing intrinsic alignment. That is a systematic error where galaxies naturally point toward each other, a physical effect that can easily be mistaken for the signal of dark energy or modified gravity. In April 2026, as the flight model undergoes final thermal vacuum testing at Goddard, scientists are preparing a 3x2-point analysis. This will combine lensing, galaxy clustering, and galaxy-galaxy lensing into a single statistically bulletproof verdict. Regardless of which model survives the scrutiny, the dataset Roman returns will be the final word on the standard model of cosmology. But as we wait for the launch, we must ask, what parts of our cosmic story are already anchored in absolute reality?
In a sea of new data and conflicting numbers, it's easy to feel like our understanding of the universe is crumbling. But foundations of modern cosmology are actually stronger than they've ever been. We are not lost. We are simply sharpening the map of a territory we've already claimed. The reason scientists speak of a crisis is precisely because our measurements have become so accurate. The cosmological concordance, the agreement between the cosmic microwave background, distant supernovae, and sound waves from the early universe, is an evidentiary anchor that isn't going anywhere. This convergence tells us one thing for certain. About 70% of the universe's energy budget is a form of dark energy that drives acceleration. We may debate whether it is a constant or a dynamic field, but its existence is a verified physical reality. Another unshakable anchor is the age of our universe. By cross-referencing the faint glow of the Big Bang with the ages of the oldest star clusters, we have locked the timeline at 13.8 billion years, with a precision of about 1%. We also know that dark matter is real and essential. Whether it's through the way galaxies rotate or the way gravity bends light in deep space, we see the fingerprints of an invisible mass that outweighs regular atoms 5 to 1. That's a bedrock observation. The crisis we discuss in April 2026 isn't about whether these things exist. It's about the fine print of how they evolve. The Big Bang isn't being canceled. It is being detailed with higher resolution than any previous generation of humans could imagine. Think of it like this. We know the universe is expanding, and we know why it began. What we are looking for now is the throttle, the specific mechanism that determines if that expansion will continue forever or lead to new physics. This boundary between what we know and what we are searching for is what makes the 2026 landscape so exciting. Projects like DESI and the Euclid mission have already provided the broad stroke maps that confirm the standard model's core, while highlighting where the edges fray. However, even these anchors have their limits. We still do not know the particle identity of dark matter, nor do we know the source of the vacuum energy itself. These are the known unknowns that define the frontier.
Critics often point to the Hubble tension as a reason to doubt everything, but in reality, this tension is the scientific method at its best. It is the friction that occurs when two extremely successful models meet at the limit of their precision. By April 2026, the scientific community has moved past the fear of being wrong. Instead, there is a focused synergy. Euclid is preparing its first major cosmology data release for October, while Roman is being calibrated to verify those findings. This cross-calibration is our best defense against systematic errors. If 3 independent missions using different hardware and methods all point to the same weakening signal, we aren't seeing a mistake. We are seeing a new law of nature.
We are standing on a platform of verified facts, an expanding 13.8 billion-year-old cosmos dominated by dark components. This standard model remains our best guide, even as we prepare to add a new chapter to its expansion history. The anchors are set, and the boundary of our ignorance is clearly mapped. Now, the only thing left is to pull the trigger on the most precise measurement in history. When does the definitive countdown to the launch begin? As of today, April 4, 2026, the physical answer to our cosmological crisis is sitting inside a high bay cleanroom at NASA's Goddard Space Flight Center. The Nancy Grace Roman Space Telescope is no longer a collection of blueprints. It is a fully assembled 6,000-pound reality. The observatory is currently undergoing its final gauntlet of environmental testing. Engineers are subjecting the hardware to the brutal acoustics of a rocket launch and the deep freeze of a thermal vacuum chamber, ensuring that every 288 megapixel sensor can survive the journey to the second Lagrange point. That journey is scheduled to begin in the final months of 2026. A SpaceX Falcon Heavy rocket will lift the observatory from Kennedy Space Center, marking one of the most high-stakes science launches of the decade, with a final safety window extending into May 2027. Once it reaches L2, a million miles from Earth, Roman will deploy its distinctive barrel-shaped sunshield. This position allows the telescope to stay in a stable gravitational pocket, keeping its infrared detectors shielded from the heat of the sun and the Earth while it gazes at the deep past. We won't have to wait years for the first results. While the primary mission spans 5 years, the Cycle 1 science program is designed to release its first calibration data and first light images by mid-2027, just months after the telescope completes its commissioning phase. The timing is critical. By the time Roman begins its high-latitude wide-area survey, the European Space Agency's Euclid mission will have just released its first full year of cosmology data in October 2026. Roman will act as the deep focus lens that verifies Euclid's wide-area maps. This synergy is the definitive tiebreaker we've been waiting for. If Euclid finds a hint of weakening dark energy, Roman's higher resolution and triple method strategy will either confirm a new law of physics or reveal a hidden systematic error in our current measurements. But dark energy isn't the only mystery on the manifest. Even if the cosmological constant holds firm, Roman is expected to discover thousands of new exoplanets through gravitational microlensing, finding worlds in the habitable zone that are too distant for missions like Kepler or TESS. It will also map the distribution of dark matter with unprecedented granularity. By observing 20 million galaxies in a single census, Roman will reveal the fine-scale structure of the cosmic web, showing us exactly how invisible mass has herded the visible stars over time. The data volume alone is a revolution. Roman will transmit roughly 1.4 terabytes of data back to Earth every single day. This flood of information will require new AI-driven analysis techniques to process, effectively moving cosmology from the era of samples to the era of big data. There is, of course, the ever-present risk of the unknown. Launch delays or instrument malfunctions are part of the gamble of deep space exploration. However, the engineering margins built into the 2026 flight model are the most robust NASA has ever attempted for a survey mission of this scale. We have seen the hints of a weakening vacuum and felt the friction of the Hubble tension. Now, we are months away from the telescope that will turn those theoretical debates into observational history. The map of the 21st century universe is finally being drawn. Will the universe remember our current laws of physics? Or is the Nancy Grace Roman Space Telescope about to rewrite the story of how everything ends? The countdown to the ultimate cosmic census has officially begun, and the first year of data is waiting. To stay updated on the Roman launch milestones and the evolving dark energy crisis, subscribe and join us as we follow the mission to L2. The next era of cosmology is almost here. Thank you for traveling through the dark universe with us.